Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today, Fabio Toninelli will tell us about metastability and logarithmic energy barriers.
So, first of all, thanks for the opportunity to give this talk here. I'm going to tell you about some work we did in Rome with Pietro, Fabio, and Hubert and François, who were postdocs there last year. Well, and so it's about the stochastic dynamics for a model of, so it's a model of coming from statistical physics. It's a 1 + 1 dimensional polymer model. I'll introduce it. And let's say, if you look at the invariant distribution, you will see that it sort of has two phases. You will see a picture in a moment. And we want to understand the dynamical signature of this two-phase phenomenon, double well phenomenon. So I will introduce the Glauber dynamics, which most of you know anyway, but just go through it quickly. And then, since we have this double well structure, we expect and actually prove results of the type that the system jumps from one phase to the other in a sort of metastable. I mean, the metastability results about the way the system jumps from one phase to the other and back. So it's somehow a very specific model. That is maybe okay. It's very specific, you will see, but the phenomena which arise are, we think, more general than the specific model, and are of some interest with respect to all the results about metastability for other systems. Okay, I will come to the discussion towards the end. So let me come to the model. The model is like that. The generic configuration of the system is a path, a nearest neighbor path, starts from -L, ends at +L, and at each step goes up or down by 1, right? So, and then there is this horizontal line, and here I've marked the point where the path intersects the horizontal line. This is, you can see it as a polymer configuration, if you want, in two-dimensional space, and it is a directed path, so that's why I mentioned 1 + 1 dimension. Anyway, so the configuration is just one of these paths, and we put a measure on it by weighting a path. So the equilibrium measure will be P, depending on the size of the system, and on some interaction parameter lambda, which is non-negative. And we just weight the path by taking the lambda to times the number of these red dots. Okay, so lambda to the number of intersection between the polymer and this horizontal line. Good, so this is n of eta. And of course, then you normalize it to be a probability. So if lambda is larger than 1, then you are giving a reward to the polymer, to this path for touching the interface. If lambda equal 1, you have just a uniform measure, and if lambda is smaller than 1, you are penalizing intersection. So actually, we will mostly interested in the case lambda smaller than 1. So penalizing, if you want, this line is repulsive. Good. So just at equilibrium, I mean, this invariant measure doesn't hide anything exotic. I mean, nothing. I'm not going to say anything new about this equilibrium measure. I mean, at equilibrium, the system is very easy to analyze. For instance, you can compute exactly the free energy, which means computing the large L asymptotics of 1 over L times the log of the partition function. This is exactly computable. You can compute the correlation function in the large L limit. I mean, this is all explicit. You can do it by renewal theory. Let me just tell you a couple of facts about this equilibrium measure. So as I said, there is a special value of lambda, which is 1. At lambda equal 1, all configurations are equiprobable. So you just have essentially a random walk condition to come back to 0 at the end. So a sort of Brown random walk bridge, if you want. And for lambda larger than 1, the configuration is typically localized, meaning that if you look at the average of the number of contacts and divide by the size of the system, this converges for large size to a constant, which is positive, depends on lambda. If lambda is smaller than 1, then this constant is 0, but you can say more than that. You can say that the probability that you have at least a certain number of k of contacts decays exponentially with k. So you have really, the number of contacts is really tight. But you can also say more for lambda smaller than 1. Not only the number of contacts is typically of order 1 with exponential tail, you can also say that they are close to the boundary. So you can say that, so take some parameter small l, which will be growing with the system size, but much less than l. And look at the configurations which are positive. Well, I have a picture just of that. No, the picture disappeared. Well, it doesn't matter. Look at the configurations which are positive at distance small l away from the boundaries, and call omega plus the set of configurations. And omega minus will be just minus the set, minus the configurations which are in omega plus. And then something one can prove easily is that the sets omega plus minus have probability essentially 1/2 for n large. So meaning that the probability of having an intersection or a zero of the random walk, say in the middle, very far away from the endpoint is going to 0 with L. So here I had a picture which said that essentially, but it's just what I wrote here, configurations are either mostly plus with few zeros at the boundaries, or mostly minus. And I will refer to these omega plus, omega minus as the two wells, the two potential wells. But okay, so for pictorial reasons. So we have these two wells on which the probability measure concentrates in the large L limit. Would like to understand what is the effect on a dynamics, which I'm going to introduce in a second. So we introduce the stochastic dynamics, which is just the heat bath dynamics for those who know it. It is stochastic dynamics, which well, okay, so it's defined like this. You have your polymer, your path goes from minus L to L. So to each point x from minus L to L, integer, you attach an independent mean 1 exponential clock to rings at exponential times of average 1. And when, okay, let me draw a picture. Okay, there is a picture here. So suppose that, so it's at this x here, the clock rings. And at that time, your configuration is the blue one. Then at that time, you flip. Well, you put to equilibrium this portion of the path, conditional on all the rest. So, just to be more explicit, if your configuration is something like this, and suppose that x is here and the clock rings. If you are at height, if the polymer if the path at that moment is at height 2, then you flip the height from like this to this with a probability which is lambda over 1 plus lambda, and otherwise, if your distance you are away from the interface, for instance, if you are here, then when the clock rings at this x, you flip only with probability 1/2. This is the more explicit way to describe this. So whenever the clock rings, you equilibrate that part of the path, given conditioning on all the rest. Of course, if the clock rings somewhere here where you cannot flip any value or mountain, you do nothing. Okay, this is the usual heat bath dynamics. So it's well known. The equilibrium measure is this measure I introduced is invariant, reversible. You have continuous time Markov process which converges to it. As long as you are in infinite volume, no problem, you converge exponentially. And we are interested. Okay, one quantity one looks at is the the relaxation time, which is just given by the inverse of the smallest eigenvalue of minus generator. Just gives you the speed of convergence to equilibrium in L2 norm. So we call this the relaxation time. So, as I said, so this is a very pictorial image. I mean, just very rough. Essentially, you imagine that the system, the configuration of the system is just a point, and at equilibrium, it is either in the this omega minus set or in the omega plus set. So it's in one of these two wells. So what will happen is that if you let the system evolve starting from somewhere, suppose in the omega minus phase, for some time it will stay there, sort of moving there but not exiting the well, and then on and then losing memory inside this phase, and then on a much longer time scale, given by the relaxation time, we will jump to the opposite phase, and so forth. So this is a very rough picture because somehow in this picture the system is one-dimensional. So if you really had a particle in one-dimensional potential with two wells, or even finite-dimensional space, you could apply the Friedel-Wenzel theory, and it would be it's standard sort of to justify what I've just said, that you spend a lot of time in a well, then after an exponential time you jump to another well, and essentially that these jumps occur at are independent. I mean, the time between two jumps are independent, exponentially distributed random variables. Now, of course, here in our case, as in many other cases like the easy model, examples I will make later, the problem is that the system lives, of course, in a very large dimensional space, which grows with L. So it's really hard to make sense of this picture. But this is, I mean, common to most non-trivial statistical mechanics systems, let's say. An additional difficulty in our case, which I will discuss a bit later, is that this picture of metastability requires somehow that there is a very large separation between the time scale which the system takes to equilibrate inside a pure phase. Let me call this T pure phase. I will not define it precisely. And the time scales which is needed to jump to the other phase. We need this separation to lose memory inside one phase. We will see that in our case, this separation is not so big. So that is why this makes things a bit subtle in our model. Good. Is it okay? So just I will just.
What if you never let it become negative?
Oh, you put the wall? Yeah. Well, then the relax. Well, so what is the question?
What's the relaxation?
Yeah, it's L squared. Well, I have a slide on that, but no, maybe not exactly on that question. So the relaxation time should be L squared. We can prove the mixing time is over at most L squared log L, and I guess for the lower one, I'm not sure we have L squared or L squared log L.
It depends on lambda.
Okay,
for large lambda, one expects even better.
Yeah, for large lambda, one expects the mixing time in that case to be L squared.
Less than 1.
The gap.
Yeah. So I have a slide just in a couple of slides. Okay, so before stating the results, given a set S, let me call tau S the heating time of this set, so the first time where you enter this set. And let us look at this rescale process, which is the following, omega of S. Omega of S is 1 if the configuration at time S times the relaxation time is inside omega plus. It is -1 if it is inside omega minus, and it is 0 otherwise. So it just tells you which well you are, and it gives you 0 if you are outside of both. Good. So the result we proved here, let's say, let me give in 3 parts. The first one says that justify this metastable picture. So we can find a set S plus inside the well omega plus, which is not exactly omega plus itself, but it has an equilibrium measure which is 1/2, apart from small correction. So it almost fills the omega plus I've just introduced. And whenever you start in this set, then the time to jump to S minus, so the opposite of this set, is exponential, and it's exponential with this rate, twice the relaxation time. Well, 1 over twice the relaxation time. And this O, so in the O of 1, it's important that it's uniform in time. Otherwise, this claim could be a bit empty. So whenever we can build two sets, S plus and S minus, altogether they have almost full measure. When you start from one of them, you jump to the second set with in an exponential time like this. Okay? So the second thing is that if you start inside S plus and you look at this rescale process omega S, then it just converges to a Markov chain on two states, plus and minus, with unit jump rates. So if you look at the system on this rescale time, so you just multiply time by relaxation time, then you are either in plus or in minus, and you make jump between the two at exponential times. And you never sort of, for fixed time, you are always inside one of the two wells. So in principle, this omega also takes the value 0, which means you are outside of both things. But in practice, you will never see it. So in words. And thirdly, we have some estimate on the relaxation time, on which I will give some heuristics, because it also explains some other of the results, which is between two powers of the system size, power 5 over 2 and power 9 over 2. So somehow it's perhaps a bit surprising that we have such a sort of precise picture without knowing, having really a good control on the relaxation time, maybe. Good. So this is a bit the picture that comes out. I would like to give before doing that, maybe I come back to the question before. So this was all about lambda smaller than 1. Maybe I just repeat it. So what happens for lambda? So the system exhibits a dynamical phase transition in the sense that for lambda larger or equal than 1, the relaxation is quicker. So for instance, for lambda equal 1, where equilibrium is just uniform on all the paths, the mixing time is known to be of order from above and below by L squared log L. So this was proven by David Wilson by coupling argument. And the relaxation time is of order C L squared with a totally explicit C. Something like 1 over 2 pi squared or something like that. So for lambda larger than 1, so you see here the relaxation occurs on time L squared, more or less, apart from logs, while in the other case, for lambda smaller than 1, we have at least L to the 5 over 2. So. And for lambda larger than 1, we have bounds in an earlier paper, which are the form between L squared and L squared log L, and the relaxation time between L and L squared. And just as a conjecture, we think that this bound, the L square bound on the mixing time and the L bound on the relaxation time, are the optimal ones. With this we can prove in a limit where the interaction parameter lambda grows with the system size. And we believe it to be true in this whole region. But anyway, so, and for the system with the wall, if it is sufficiently attractive to keep to have localization, we also conjecture these things to be true. Anyway, but this was mostly to show that for lambda in the localized or in the neutral, we could call it phase, so either lambda equal 1 or larger, there is really a different scaling of the relaxation time with respect to lambda smaller than 1.
There were early papers by Randall et al. That like L to the 20.
Yes, they showed actually
With the wall.
Yeah, it was a system with a hard wall constraint. But probably you can extend that to get L to the something. Yes. So, so let me for a moment abandon this. I mean, I would like to explain first of all why this 5 over 2 appears, and also a bit like what are these exponential these logarithmic barriers I mentioned in the title. So. You have a system, so suppose you start the system inside the phase omega minus. So you have a configuration which is mostly negative, and eventually you know it will jump to omega plus. So what is a reasonable way for the system to do that? And you have to remember that this horizontal line is repulsive, so you don't want to touch it too often or too much. So a reasonable way is that the system creates a sort of bubble here at one of the two sides of the system, let's say on the left. The end point of the bubble, let me call it C. Then this bubble will fluctuate, enlarge. So this C will move, fluctuate back and forth, and then in the end it will move to the right boundary, so the bubble has just expanded to everything, so you have jumped to the plus phase. Okay, so this is a reasonable mechanism. Of course, it's if you somehow it will not exactly happen like that. You can create more than one bubble, but for the purpose of these heuristics, let's disregard that. The reason being that, as I said, at equilibrium, it's very unlikely to have many intersections, to have many zeros. So this decays exponentially with number of zeros. So it's reasonable that even during the dynamics, you have no reasons to create many of them. So let's just suppose there is one of them, one of those. Good. So then the second observation is that if you look at equilibrium, what condition on having exactly one bubble, so having one crossing, what is the probability that at equilibrium that it occurs at some point x? If you do the simple computation, you will see that its probability behaves like some normalization factor times 1 over the distance of this xi from the left boundary to the power 3 over 2. And then by symmetry, there is also 1 over the distance from the right-hand side to the powers minus 3 over 2. So you can see, you can write as being this xi as being a particle in a potential v, which is of this logarithmic form. It grows logarithmically from the both endpoints, and okay, then there is this sort of shifting just to normalize the measure. So the potential is down like this. And in the middle, the potential is 3/2 log of L. Okay. So then, again, arguing heuristically, you believe one imagines that these endpoints of the bubble will fluctuate back and forth, but it will try to go down towards the minimum of the potential. So it will feel a drift, which is just given by the gradient of this potential. So the gradient will be, if the xi is in the first half of the system, will be something like minus 3 over 2 the distance from the left-hand side, and otherwise symmetrically in the second half of the system. Somehow in this whole heuristics, there is a hidden conjecture that along the evolution, these two bubbles stay at equilibrium conditionally on the position of xi, which is something we cannot at all justify. But it's sort of reasonable. This xi should give you sort of the slow mode, and then the two bubbles should follow and equilibrate themselves along the way. But it's very hard to justify. Good. So let's see what comes out from this kind of heuristics. So first of all, you have this particle xi which feels a drift, but the drift is almost zero in most of the system. It decays like 1 over the distance from the endpoint. So if you are at the macroscopic distance from the endpoint, the drift is almost zero in a sense. The second is that the potential barrier, which is in the middle, is logarithmic in the side of the system. So like 3 over 2 log L. And there is some connection between this bubble dynamics and the zero-range process introduced by Landim and Beltran 1 year ago, but I will not define this system. And then the last observation is that there is a non-trivial competition between a diffusion effect and an activation effect. So what is that? So consider to look at these two pictures. In the first one, you have a particle which moves in a potential which grows. It's still between L minus L and L. The potential grows linearly in the first half of the system, then decreases linearly. It's symmetric. So it will feel a drift, which is just the slope of the potential, which is V. Here it goes to the left. Here it goes to the right. In the second picture is the one we are looking at. The potential is logarithmic, and the drift is what I had just before. And the barrier, so barrier here is linear in the size of the system, and here is logarithmic. So what is the time this particle will take, if suppose you started here, to jump to go to the other endpoint? So first of all, suppose there is no potential at all, then you have just a simple random walk between minus L and L. It will take a time L squared, just diffusion. Now, secondly, in the case of uniform drift, I mean this minus V plus V, then so the time to jump a barrier of height V0, which is V times L, is sort of is essentially the exponential of this barrier height. One can see that this is true. It's not difficult. So usually, I guess this is called something like activated dynamics. To jump across an energy barrier E, you need exponential of E, and then there should be betas like temperature. But here there's no temperature. Okay, so what in our case? If you believe in this kind of picture, you would guess that the time to jump from one endpoint to the other should be exponential of the barrier, which would give you L to the 3 over 2, which clearly is wrong, because already without potential, we know that the time is L to the L squared. So there is a sort of competition between this diffusion effect and this activation effect. And for this one-dimensional dynamics with this drift, the relaxation time can be computed exactly apart from constants. For instance, using a method by logarithmic law, using Hardy's inequality, or by using canonical path. Anyway, you can compute this, and the relaxation time turns out to be L to the 5 over 2. And personally, I don't have a very clear heuristics on just looking at the system why the 5 over 2 should come out. Anyway, so this is about this simplified dynamics. One bubble approximation, local equilibrium, blah, blah. Yes?
But is the 5 over 2 just some function of 3 over 2? Or is it
It's something. No.
The whole function it is.
No.
5 thirds times.
No, it's not so complicated. I guess it's. I think if the potential were just 1 over x, I mean, alpha log x, maybe it's alpha plus 1 or so something. It's a linear.
You sound.
Yeah.
No, it's a simple function. So nothing exotic. It's just that, it's not so easy to guess, I think. So anyway, this heuristics is something we find a bit rather convincing, so we conjecture this to be true. And for the true dynamics, so let's forget this one-dimensional one.
I'm sorry, can I just drag
Yeah.
you back 1 second? I mean, the exponential would have broken down for sufficiently small constants. In other words, constants that aren't constants, which is sort of what you're looking at here. Anyway, I mean, your prediction of 3 halves would have broken down for C, wherever you had the exponent going to 0. So, why was 3? If you want to go back a little bit. If V naught is 0, your formula is wrong, and 1, 2. So it's sort of misleading to
I mean,
say that it predicts 3 halves.
I agree. No, I mean, I agree. I mean, but.
No, so if you set the constant such that, I see. Then you get 3 halves just by plugging in, pretending it was a straight line.
I mean, I was just.
Yeah.
No, I agree.
It's
It was a
not only about
misleading
the height of
argument.
The
The shape is important.
Yeah, the shape is important. That's
Not all of that.
But so maybe just to in the case where when the drift is constant, is the minus b plus b. So the picture is really that the particle spends a lot of time to the left, then at some random time, exponential time, decides to go to the other side, but not slowly, not with
Just
like
linearly.
a random walk. Takes essentially a drift that is plus b to the right, goes to the top of the mountain, then falls down. Okay? So here certainly the system is doing something, intermediate.
So what altitude can you make that statement about? I mean,
I see.
how high does V naught have to be before you can make this, what you
So
said?
instead of 3 over 2 log L, maybe 100 log L, then it works. Yeah, okay.
Well, but even what you said is not the whole thing, right? Because many times it climbs halfway up and that goes back.
No, not many times. Very few times.
Yeah, exactly. Yeah.
Exponential and L over 2.
What?
So-
But
so-
that
yeah,
that's
almost,
lost to the
yeah.
to the L.
No, it does it. Exponential and L over
Yeah, but
2 times
yeah,
before it does
yeah.
the whole thing.
Yeah, but the last
The total
excursion is very quick. Occurs on
Yeah.
with the positive velocity. Okay,
Yeah.
so because it's so costly to be in the middle.
average distance that goes on these experiments stays bound before it makes the big.
Okay. as I said, for the true dynamics, we proved these two bounds. We believe the lower one to be correct based on these heuristics. And
both of them to be correct, but the lower bound to be sharp.
thank you. Well, we hope both will be correct. No, I mean, no. The reason why we get this 9/2, it's better to see it as 5/2 plus 2. And the reason is that we use some decomposition for Markov chains. So the point is that the slow mode, which should give you the correct mixing time, is the motion of these bubble endpoints. Well, there will be more than one. So that should give you the 5/2. And then the motion of the excursions given the bubble endpoints should be diffusive, like a single excursion with a wall. That should give you L to the 2. So by this decomposition method, instead of finding the maximum between them, you find the product. So that's why we lose a 2. So, but already giving that is quite a technical pain. But this explains the 9/2. So yeah, let me come to this question about the not so big separation of time scales. So the difficulty which appears is that the time to relax inside the single phase is of order L squared, so which is not much smaller than N to the 5/2, which we believe to be the time to jump from one side to the other. Okay, it's much larger, but only by square root of L. So for instance, one thing we can prove is that if you look at the evolution starting from the maximal configuration, which I denote by this sort of tent, so maximal configuration would be a path down like that. Cannot having anything higher than that. You look at the evolution at time t, this is the semigroup. And then look, what is the difference from just looking at the plus phase? Plus phase meaning you take equilibrium condition to be positive. Then if you look at this at time much smaller than L squared, you are at distance, in variation distance, essentially 1. You have not moved in variation distance. If you take times which are sufficiently larger than 2 and sufficiently smaller than L to the 2 and L to the 5/2, then this variation distance is smaller of 1. So in this time range, starting from the maximal configuration, you have relaxed to one of the two phases, well, the one where you start from. So this is so we are able to prove it starting from the maximal configurations because we use a lot of monotonicity arguments which do not work for a given arbitrary configurations inside omega plus. But it's morally, this should be true for most configurations in omega plus, just that we cannot prove it. Anyway, so this proves that this T pure phase I have not defined is of order more or less L squared. And as I said, the global time should be over the L to the 5/2, so which is not so distant. So in the beginning, we were not even sure that this separation would be enough to have, at least to be able to prove metastability. So let me just, in contrast, let me recall that another well-known case where metastability has been proven is that 2D is the model with free boundary condition. You are below the critical temperature, so you have two phases, plus, minus. And then also there, you start from, let's say, the all plus configuration in some time which is of order, well, this is not really proven, but let's say more or less. In a time of order, a power of the system size, you will converge the plus phase, which is the one close to where you started from. And then on a much larger time scale, you will jump to the minus phase. And this time scale, which is of the order of exponential of the size of the system, where the constant here is related to the surface tension. So very quickly, you converge to one of the two phases, then it takes enormously longer to jump to the other phase. And having these this big separation allows Fabio and Marcelli to prove this metastable picture. So here we don't have this lot of time to lose memory. This is the difficulty. So essentially, well, okay, it was said 30-40 minutes. So I can just flash one slide to just give a few ingredients of what we do, and then if anyone is interested. So one ingredient is proving that from the maximal configuration in time L squared, more or less, you converge to half of the equilibrium, so the plus phase. The second one is the mixing, as I say, the relaxation time is the lowest eigenvalue, blah, blah, the inverse. So there must be some function which solves generator times g equal minus 1 over the relaxation times time g. So and then one step is proving that there exists. We cannot prove that that you have a simple solution, but there exists a solution to this which is close to indicator of the plus phase minus indicator of the minus phase. And from these two ingredients, it's almost easy to prove that starting from the maxima configuration, looking at things at time of order Tyrrell, then the distribution looks like this. You are in the plus phase with this probability, in the minus phase with this other probability. And then this is, let's say, the first step to prove metastability. The rest is definitely more messy. So maybe I stop here.
Questions or comments? Do you have more slides for those of us?
Yeah, I pretend that I had more, but I don't.
So we need to decide to stop pretending.
No, I mean, if we can discuss on the whiteboard for those who are interested in the details. But.
Okay. So any other personal question? Thanks, Fabio, again.